Welcome back. So here we are at the end of this chapter. So everything we have learned about electron configurations, for example, if we have something that goes 1s2, 2s2, 2p6, 3s2, we know that that element has three energy levels. Level 1, level 2, and level 3, all the way to 3s2. So all that we're going to use it now to make sense out of the properties of the elements on the periodic table. So we're gonna say that we're gonna talk about the periodic trends, specifically about the atomic size, the ionization energy, and the metallic character. The atomic size is nothing more than starting from the nucleus all the way to the valence shell. That radius is what we call the atomic radius. And we can see that something that goes from here to here compared to something that goes from here to here will have an atom being larger than the other. So the bigger the atomic radius, the bigger the atom. And that's going to be based on how many energy levels we have. And other things that we're going to see very soon. What about the ionization energy? So for example, that is an atom of sodium. This is an ion of sodium. What's the difference? The difference is that it has a charge. So it's an ion. So what we're talking about is the energy required to make an ion. And how do you go from sodium to sodium plus? You have to lose an electron. So ionization energy is the energy required to remove an electron. And you're going to only remove the ones that are farthest away from the nucleus because the nucleus is not holding them as stronger as the core elements. So we're only dealing with the valence electrons. So ionization energy is the energy required to remove a valence electron. And by removing a valence electron, you create a cation. So let's think about that. So if I have an atom that is like this compared to one like this, we can say that the radius for number one is bigger than number two, right? So we basically saying this is the big atom and this is the small atom. However, let's remember what's on the center. What do we have on the center? On the center, we have the nucleus. And the nucleus is made out of protons and neutrons. So the nucleus is going to be positive. So on the center, you have a positive nucleus. On the farthest away energy level, you're going to have an electron. So the strength holding this electron together is higher than the strength holding these two together because it's farther away from the nucleus. Remember, it's being shielded by the core electrons. So you have your nucleus, and all of this here is the core electrons that are being shielded by the nucleus. So the ionization energy is going to be the energy required to remove the valence electron. So the one that is closer to the nucleus is going to have a higher ionization energy than the one that is not that close to the nucleus. So the bigger the atom is, the valence electron is going to be farther from the nucleus, so it's going to be easier to remove it. So therefore, a lower ionization energy. And what about the last one, metallic character? Well, if you recall, on the periodic table, you're going to have something like this. You're going to have your two columns on the periodic table. Then you're going to have your block over here, right? And then you're going to have your other 6 columns over here. And down here, you're going to have the inner transition metals. So if you remember, we got the steps that defines the non-metals from the metals. So the farther you are to the left, the more metallic your element is going to be. Remember over here, on the last group, those are my noble gases. So those are gases. So that's why those are going to be the less metallic. So as we move to the left, you're going to have the more metallics because that's where the metals are. But what about if you're moving down a group? How do you know which one is more metallic? Well, the way to see that is by going back to the size. Metals like lithium, sodium, potassium, and so on, they like to lose electrons. So as you go down on a group, the atomic radius is increasing, right? Because you have more energy levels. So if the atomic level is increasing, that means the valence electrons are going to be farther from the nucleus as you go down a group, which means the ionization energy is going to be smaller, which means it's easier to remove an electron. And what does metals like to do? Metals like to lose electrons. So as you go down the group, it's easier to lose electrons, so you are more metallic. And that explains the three terms that we're talking about. The atomic size, the ionization energy, and metallic characters. And you can see how all three are related to each other. So let's do some problems. So choose the element with the larger atom from each pair. So we're doing aluminum, which is right here, compared to indium, which is down here. As you notice, aluminum is located on level 3, while indium is located on level 5. So if I have something with one level, 2 levels, 3 levels, compared to something with one level, 2 levels, 3 levels, 4 levels, and 5 levels, you can see that as you go down the group, they're going to get bigger. So indium is going to be the bigger one, just because you are increasing the number of energy levels. As simple as that. What about silicon? Compared to nitrogen. We see that silicon is on period 3, nitrogen is on period 2. Just because of that, silicon is going to be bigger because you have more energy levels. The analogy I like to do is if I put on 3 jackets and then another day I put on 7 jackets in top of each other, where do I look bulkier or bigger? With 7 jackets, more layers. So imagine you can see the energy levels or the periods as adding layers into the atom. What about the next one? The next one is going to be phosphorus and lead. Clearly, we can see that lead is going to be the bigger one. And what about carbon and fluorine? Carbon is going to be here, and fluorine is going to be there. If you notice, both of them are going to be on level 2. So it's going to be a situation like this. You're going to have one energy level, 2 energy levels for one of them, and for the other one, you're going to have exactly the same thing. 1 energy levels, 2 energy levels. So how do we know which one is the bigger one? Well, carbon is atomic number 6. That means it has 6 protons on the nucleus. While fluorine is atomic number 9, which means you have 9 protons on the nucleus. So if I ask you which nucleus you think is more powerful, the 6 plus or the 9 plus, and you will most likely say the 9 plus nucleus is more powerful. It's a bigger magnet. So that means that this electron on the valence shell is going to be attracted by a stronger force on this one versus this one. Because of that, this energy level is not going to be there. This energy level that we're going to draw here is going to be closer in. So the energy level in fluorine, the energy level in fluorine, because the nucleus is stronger, is going to come inward, therefore making fluorine the smaller one and carbon the bigger one. So in terms of the size, as you go down the group, because you are adding energy levels, the atom is getting bigger. In terms of the periods, as you are adding more protons, that's going to put in the valence electrons, making it smaller. So it's going to grow from top to bottom and from right to left. The closer you're to the right, the smaller it's going to be, as long as we're talking about the same period. What about the ionization energy? To do that, we're going to find out which one is the bigger one first. So arsenic is going to be here, and bismuth is going to be here. So bismuth is the bigger one. So the electrons, the valence electrons are going to be farther from the nucleus. So those are going to be easier to remove. So it's going to be harder or higher ionization energy on arsenic. Arsenic and bromine. Since arsenic and bromine are on the same period, based on the energy levels, they are the same size. However, bromine has more protons. Arsenic is 33, bromine is 35. So bromine is going to put in the valence electrons closer, which is going to make it harder to remove them because they're going to be closer to the nucleus. So bromine would be the one with the higher ionization energy because it's harder to remove the electrons. What about silicon and iodine? Silicon is going to be here, and iodine is going to be there. So that one is kind of a little bit harder to say because they are not on the same group, they are not on the same period. We know that as they move to the right, they're gonna be smaller. However, silicon is on level 2, a little bit bigger, but the levels would always take priority over the amount of protons on this case. So I would say that iodine is the bigger one. And I'm saying that with reservation because we don't have enough information to decide 100%. So let's check that out real quick. So actually, sorry, it wasn't silicon, it was sulfur. Silicon would have been a bad comparison. So okay, so let's try sulfur then. Sorry for that. So sulfur and iodine. Well, sulfur is a little, same situation more or less, but sulfur is a little bit closer to iodine because it's on the just one group before. So I would still say that silicon is the biggest one. So sulfur should be the one with the higher ionization energy. But let's double check that. Let's see what we have in here. Let me find something here quick. I can find more information. Let me see if I have that in here or not. Just hang in there for a second. Trying to see if I have this application here. And no, I don't see it. So let's check the internet. Ionization energy for sulfur. So the ionization energy for sulfur is going to be 10.36. What about iodine? 10.45. They're pretty close. Actually, iodine happens to be a little bit smaller. So let's make sense out of that. So sulfur is on level 3, while iodine is on level 5. So I was saying that iodine was bigger, so it would be easier to remove the electrons. So sulfur will have the higher ionization energy. And that was true, but it was very, very close. So the fact that they're not on the same group makes a difference. But we were able to still get it the right way. So most of the problems you're gonna have are gonna be either the same period or the same group. And if they're not, then let me know what you're thinking. Because that's why it's important here, to think about it, not just to get it right. So what about sulfur and antimony? So if we compare sulfur and antimony, then we can say, well, sulfur is on level 3, so it should be smaller, and it's more to the right than antimony. So I would say sulfur is the smallest one. So sulfur will be the one with the higher ionization energy. So this one have the tendency, we can say, is smaller because of the period and also smaller because of the group. And if you find which one is the smaller one, then it's going to be harder to remove the electron from that one. So that will be the one with the higher ionization energy. And what about metallic character? Between strontium, which is a metal, and antimony. Therefore, strontium is more to the left. That's where the metals are. So strontium is the more metallic. What about arsenic and bismuth? They are at the same distance from the left, so that's not what we're going to use. So we know that bismuth is bigger because you have more energy levels, therefore easier to remove the electron. That's what metals like to do. They like to lose electrons. So bismuth will be the more metallic. What about chlorine and oxygen? We know that none of those is a metal, so let's see how we do this one. Chlorine and oxygen. We can say that chlorine, which is more to the right, would be the less metallic, so oxygen would be my more metallic one. You can also say that chlorine being on level 3 is probably a little bit bigger than oxygen. So more easier to remove the electrons, so more metallic. And what about sulfur and arsenic? Sulfur is here, and arsenic is over here. Arsenic is more to the left, and it's also bigger, so therefore definitely arsenic would be the more metallic because it's easier to remove the electrons for the fact that it's bigger. You can also say, let's do it on a more advanced way. Sulfur is neon, 3s2, 3p4, while arsenic is argon, 4s2, 3d10, 4s3. If sulfur was going to lose an electron, it would look like that at the end, 3p3. If arsenic was to lose an electron, it will look like this. Actually, sorry, what a monstrosity I just did in there. Not 4s3, 4s3, but 4p3. Sorry. So if this was going to lose an electron, then you will end up with 4p2 on this one. So one way to see this is which one will benefit more from losing an electron. One thing that we haven't discussed but is mentioned in Alex is that in electron configuration, having the orbital full, 6, or halfway full is a good thing. So that will tell me that by using the electron configuration, sulfur will be the one that can lose the electron easier because it gives me a more favorable electron configuration, which is half full. So let's find out. Let's see, because that's not what I told you. I told you based on size, I told you that arsenic would be the more metallic. Based on electron configuration, it's telling me that sulfur will be the more metallic, losing the electron faster. So let's check the ionization energy. So sulfur is going to be sulfur is going to be 10.36, while arsenic it's going to be 910.7. So arsenic is still going to be, yeah. So based on size, we got it right based on size. So arsenic would be the bigger one, therefore can lose the electron easier. So in this case, being so close on the piece for P3 and P2, this reasoning will not work on this case. So we're gonna stick with the reasoning on the size instead of using the quantum theory. So based on the size and how close it's to the left side, arsenic will have to be the most metallic. And with that said, you should be able to do this daily work, dealing with the atomic size. After you do that one, you should be able to do this one, dealing with the ionization energy. And after you do that, you should be able to do this one, more ionization energy. And then this one that discuss metallic character. And once you do that, we have covered the most important periodic trends, such as atomic acid size, ionization energy, and metallic character. And with that, we bring this chapter to a close. And real quick summary of what we did. We talk about light, the electromagnetic radiation, the frequency, the wavelength, and the energy. So we compare those based on the spectrum diagram that we were using. We saw how light relates to the atom, and we came up with the model atom of the atom for the Bohr's model. And then we saw how the Bohr's model wasn't good enough because it can only work for hydrogen, but it's good to explain how everything works. But then we came up with the quantum mechanical theory on a very, very, very simplified way. It's a lot more involved than that. And then from there, we learned how to do electron configurations, the full electron configuration. Then we did it with an overgassed. Then we identified the valence electrons and the core electrons. And finally, we related everything to the periodic trends: atomic size, ionization energy, and metallic character. And like I said, with that, we came to the end of the chapter. So let me know if you have any questions. You always know where to find me, email, or come see me at the office. And have a great week. Take care.